In this video, we look at the derivations of the the derivative of the natural log function in log base a of x using implicit differentiation. We'll also look at the graphs of the natural log of x and its derivative and log base a of x and its derivative. But here are some things that are known. We know that the derivative of e to the x is e to the x.
Oh.
And we know that the derivative of a to the x is natural log of a times a to the x. So since we know those and we don't know the derivative of natural log of x yet, we can start with y equals natural log of x and say, okay, I'd like to get rid of that logarithm on the right-hand side because I'm trying to find the derivative of that function. And I'd like to write this equation in terms of exponential functions. Well, I can exponentiate both sides and we'll have e to the y equals x. I don't know the derivative of natural log of x yet. I do know the derivative of e to the y using implicit differentiation. So now we can differentiate implicitly and try to find that derivative of the original function that we started with. So we'll differentiate both sides with respect to x, treating y as a function of x, because y is actually natural log of x. And here we have to use the chain rule. The derivative of e to some power is e to that power times the derivative of the inside. And the derivative of x is 1, of course. So dy dx is 1 divided by e to the y. And what is e to the y? E to the y was x. So dy dx is 1 over x whenever y is natural log of x. So that tells us that the derivative of natural log of x is 1 over x. So graphically, the way I have a tendency to graph this is I say natural log of x looks like this. When x is 1, we get 0. And if y equals natural log of x like this. But the way this is drawn, it sort of indicates that y equals natural log of x continues to increase. As x increases, natural log of x goes to infinity. So we know that the limit as x goes to infinity of log of x is infinite. But this graph might be misleading a little bit. You might think that the slope is kind of large from the way I've drawn it. But if we look at the graph on a graphing calculator or computer, you can see that it actually kind of flattens out. When x is equal to 100, let's say, the slope is 1 over 100. So the slope is still positive, but it's just very, very, very small. And if we look at the graph of 1 over x, we can see that the function values are very small. As x approaches 0 from the right, natural log, or as x approaches 0 from the right, 1 over x approaches infinity. At x equals 1, we get 1. And then as x goes to infinity, we get 0. So y equals 1 over x. If I'm just looking at the part of y equals 1 over x that is for x greater than 0, which is what we're interested in when we're talking about the natural log of x, which is that's the domain of natural log of x. We can see that the slope is very, very large and positive here, which is consistent with the function values on y equals 1 over x. But what we're saying here is that as x goes to infinity, while natural log of x continues to increase, it just doesn't increase very fast at all. This slope gets smaller and smaller and smaller, gets closer and closer to 0 as x goes to infinity. So we could see that on a graphing calculator, but we've just drawn it. But this is how we can see it or derive that formula using implicit differentiation. Similarly, we can find a rule for log base a of x, by exponentiating both sides. Since these are inverse functions, they undo each other, and we'll have a to the y on the left-hand side equals x on the right-hand side. We differentiate both sides with respect to x. The derivative of a to the y is natural log of the base times a to the y power. So you're substituting that inside function back inside, and then you multiply by the derivative of the inside by the chain rule. It's also known as implicit differentiation because the variables don't match. And the derivative of x with respect to itself is just 1. So dy dx is actually equal to 1 divided by natural log of a times a to the y. But a to the y is x. So again, you're going to see the same trends with the derivative of a to the y, or excuse me, the derivative of log base a of x that you see with the derivative of natural log of x. Because remember, y was actually log base a of x. But there's an extra factor of natural log of a in the denominator. And depending on the value of a, that could be positive or negative. It's positive when a is greater than 1, and negative when a is between 0 and 1. And it's a number that's less than 1 when a is between 1 and e, and then it's greater than 1 when a is greater than e. Let's look at these. Let's graph this function. Get some geometric intuition to back up our understanding of the derivation. So here's a graph of natural log of x on the graphing calculator. With everything drawn to scale, where 1 unit in the x direction is the same as 1 unit in the y direction, you can see that function is growing, but it does seem to flatten out. The slope does seem to get very small relatively quickly. If I plot a point, x, natural log of x, and then I draw a tangent line through that point, we can see at x equals 9.3, according to our formula, the slope should be 1 divided by 9.3, 1/9. So you go up 1 and over 9. So you can see that's going to be a very, it's not horizontal, obviously, but it's not very steep. And as x increases, that line just gets less steep, or less steep. Like here, when x equals 15, the slope is 1/15. So it's just really starting to flatten out, but it's still increasing, the whole time. So that's the idea. You can, if you want the exact value for the slope, you can also graph the derivative and then find the function values of the derivative there. 1 divided by 5.81 is our slope. So and the calculator tells us that's approximately 0.172. When x equals 10, our slope is 1/10. When x equals 14, our slope is approximately 0.072. Like it's tiny. It's very, very tiny. And so when x is 100, that slope is going to be 1/100. It's very, very small. But the function is continuing to grow. So that's true for a log base e of x. But let's look at a different base. Let's look at maybe log base 5 of x. Log base 5 of x grows even faster because the derivative ends up with this extra, or how do I say it? It's like grow faster. It sort of flattens out even faster because we have this extra factor of a log or natural log of 5 in the denominator here. Do you see the relationship between that or those two graphs together? And then these two graphs. So there's log of x and 1/x. And there's log base 5 of x. And the derivative of log base 5 was just 1 divided by natural log of 5 times x. So they're very similar. They're just off by this extra factor. And I think you can see it if you compare just log base 5 of x to e to the x in general. when I look at log of x, we're gonna get 1 for our function value when y is equal to e. So we can plot the point e and 1 on that graph. For log base 5, if we plug in 5, we get 1. So it just, like if we were drawing the exponential function, the log base 5 would grow much faster. But since we're sort of turning it on its side and we're switching the roles of x and y, I guess this one flattens out faster, if that makes sense. The slopes get smaller faster than the slopes of this one do. Hope that makes sense. But that's the idea. In the next video, we'll look at the derivations of the inverse trig derivatives.